Hello everyone! You have learned how to make an energy balance based on heat transfer through transmission, ventilation and infiltration, solar heat gains and internal heat gains, and based on solar radiation and indoor and outdoor temperatures. Well, that is very nice, but how is this going to help you with the design of buildings' energy systems? Well, that is what this lecture is about. When designing the energy systems of a building, there are two things we are really interested in. The first one is to be able to choose the right size of the heating and cooling equipment, what we call HVAC, heating, ventilation and air conditioning. By the right size, I mean, for instance, that you don't want to buy a too small boiler and then have an uncomfortably cold building in winter. But you also don't want to buy it too big, making high costs for nothing. The second thing you really want to know is about the energy demand and how to minimize it. In the end, this energy demand will determine your energy costs or energy bills together with the efficiency of the chosen equipment. In this course, we don't look at the equipment, but only at the energy demand. This will be the subject of another lecture. This lecture is about the sizing of space heating and cooling equipment and about how the energy balance will help us doing that. When we talk about size, we talk about the maximum power that should be delivered by the equipment. It is power, so the unit is watt or kilowatt. You can compare it again to a water tap. If the tap is too small, there will be only a little bit of water flowing through it, meaning that it will cost a lot of time to fill the bucket. If you want to make sure the bucket is filled within 1 hour, equivalent to the quantity of energy we need to have in that hour, then you need to buy a tap that allows for enough flow rate. So, this maximum power is also referred as nominal power or nominal capacity or nominal load. It relates to the costs and the physical size of the equipment. To make this clear, I have chosen the example of gas heating boilers to show you their price and size depending on their nominal powers. Here left 18, 60 and 150 kilowatt. You can see that the price and dimension both increases with the nominal power. How to choose the right size of the space heating and cooling equipment. We will look at two different methods. The next 5 slides are about the first method. Basically, the heating equipment should deliver enough heat for the hour of the year with the highest heating demand, while the cooling equipment should deliver enough cold for the hour of the year with the highest cooling demand. Let's start with the heating equipment. You know everything about the energy balance and the effect of transmission, ventilation, solar and internal heat gains. Take 3 seconds to think about the weather characteristics relating to this hour with the highest heating demand. What are they? Well, for sure, that will be the coldest hour of the year, maximizing the transmission and ventilation losses. And probably it will be at night with no solar gains at all. And to have some margin, we can also assume that there are no internal heat gains. Let's look now at the cooling equipment. Take again 3 seconds to think about the related weather characteristics. For sure, there will be probably a combination of a maximum of solar radiation, highest outdoor temperatures, and a lot of internal heat gains relating to high building occupancy. Let's start with the highest heating demand, the so-called nominal load for space heating. We said we should consider the lowest outdoor temperature and no solar radiation or internal heat gains. If we take our energy balance in watt-hour, this means that energy for internal heat gains and solar radiation is 0. It also means that the transmission and ventilation and infiltration energy should be calculated for this lowest outdoor temperature, TO min, in the slide. And finally, we make the balance to find out the nominal heating energy, which is the energy needed during this coldest hour. That's the last equation on the slide. We start again with this equation in watt-hour. What we want for sizing are watts, the energy flow rates. So we only need to divide by 1 hour to get the formula for the nominal power. Let's take the example of a small apartment located in the Netherlands. You see its dimensions on the right, and from its ventilation and construction properties, we have derived that the sum of all UA values for the transmission losses is 7.8 watt per Kelvin, and rho VCP is 53.6. We want to achieve an indoor temperature of 20 degrees C. To be able to estimate the nominal power, we need to know what is the lowest outdoor temperature in the Netherlands. Well, we can look at meteorological data. That's a good way. In many countries, there are also building codes stipulating the coldest temperature to choose. In the Netherlands, that is minus 10 degrees Celsius. So, now we fill in this data to calculate the nominal power and come to a power of 1.8 kilowatt. So, if I want to buy a boiler for this apartment, I will choose one with a nominal power around or a bit above 1.8. If I want to buy a heat pump instead of a boiler, I will do the same. And if I want a connection to district heating, I will take care that this connection has a power of 1.8 kilowatt. And of course, I can make price comparison between different types of heating and different suppliers. Let's continue now with the highest cooling demand, the so-called nominal load for space cooling. We said we should consider the highest outdoor temperature and the maximum solar radiation and internal heat gains. If we take our energy balance, this means that we need to calculate the energy for internal heat gains and solar radiation, and also the transmission and ventilation and infiltration energy for the highest outdoor temperature, TO max, in the slide. And finally, we make the balance to find out the nominal cooling energy, which is the energy needed during this very hot hour. That's the last equation on the slide. And it is negative because it is cooling. We start again with this equation in watt-hour. What we want for sizing are watts, the energy flow rates. So we only need to divide by 1 hour to get the formula for the nominal power. You will notice here something new, which is that we are now using the absolute value of the cooling heat flow. According to the conventions, it should be negative, meaning that it is a heat flow being removed from the building. But from now on, we will express it as a positive value. This is the habit in the field, as everyone knows that cooling is removing heat. But of course, please don't forget to put again the negative sign in all balance equations when making calculations, just as you have learned. Only the result is taken as absolute value. Let's take the same example as in the heating load. A small apartment located in the Netherlands, of which we know the sum of the UA values and rho VCP values. We want to achieve an indoor temperature of 24 degrees because it is summer and a temperature of 20 would be experienced as much too cold. To be able to estimate the nominal power, we need to know what is the highest outdoor temperature in the Netherlands. Well, it is around 30 degrees C. We also need the maximum solar radiation on this south-oriented window. In the Netherlands, that will be 800 watt per square meter. So, now we fill in this data to calculate the nominal power and come to a power of 2.2 kilowatt. So, If we want to buy air conditioning, which is the same as a cooling machine for this apartment, we need to choose one with a nominal power around 2.2 kilowatt. Based on that, we can make price comparisons between different suppliers of cooling machines. This first method is very useful and easy as it allows you for making very quick calculations based on what you intuitively know from your own climate. However, it may lead to oversizing the heating and cooling equipment, which may be mandatory in the building code of your country, but it is good to be aware of this possible oversizing. Method 1 may lead to oversizing the nominal heating load because in typical years an outdoor temperature of -10 degrees almost never occurs. By choosing a more commonly occurring minimum temperature, we could reduce the size of the equipment and therefore the costs, while taking a limited risk that once in a few years the indoor temperature will be a bit colder than 20 degrees. As it comes to the nominal cooling load, the oversizing will be large for two reasons. First, the highest outdoor temperature does not necessarily occur at the same time as the maximum solar radiation. And second, you may remember that when describing solar heat gains for the energy balance, we neglected the time delays resulting from heat absorption in the construction mass. So, for a proper estimate of cooling loads, we would need a dynamic model, which is not the subject of this course. However, making static balance calculations per hour over a whole year using meteorological data representative for the real weather would already be helpful. You see here left the results of such a calculation where we have plotted the heating loads all over the year. Basically, we made the same balance calculation as you did last week, but did it 160 times the number of hours of a year. You see here that the maximum power is obtained somewhere at the end of the year and has a value of 1.64 kilowatt. This is a bit less than the value we calculated with method 1, which was 1.8. This is because the minimum temperature occurring in our representative weather data file is -7 degrees instead of -10. In the graphic on the right, you see now the resulting absolute values for the cooling loads. You see here a lot of cooling in summer and nothing in winter. The maximum value, which is the nominal cooling load, is 1.77 kilowatt, which is substantially less than the 2.2 kilowatt found with method 1. To summarize this lecture, you know now that the nominal power for heating and cooling is what we call the size of the equipment. It relates to physical size and price. The nominal power for heating is determined by making an energy balance for the coldest hour of the year, neglecting solar and internal heat gains. The nominal power for cooling is determined by making an energy balance for the warmest hour of the year and with the highest solar radiation and internal heat gains. With this method, which is often compulsory in building codes, both the heating and cooling load may be overestimated. Carrying out calculations based on representative weather data may give a more accurate result. The nominal powers are then the maximum powers obtained for heating and cooling when considering a complete year.